In sections 1.1 through 1.4, we've explored different voting systems. We've looked at plurality, plurality with runoff. We've looked at the border count method, Condorcet winner, approval voting, a whole bunch of methods. And the question is, do any of these methods lead to a really good system of voting? Or maybe even a bigger question we could be asking is whether there is such a thing as an ideal voting system. So we're going to explore that question a little bit in section 1.5. And specifically, the work that we're looking at is in large part due to Kenneth Arrow, who won a Nobel Prize for this. And Kenneth Arrow formulated an approach to ordering choices among public policies. And so if you think about ordering choices, that could sound a whole lot like an election where you rank your choices. So any election system where it is based on a ranking of the choices, Kenneth Arrow's work will apply. And of course, if you think about the voting systems that we've talked about, even plurality voting is based on ranks, because in a plurality system, everyone votes for the candidate that is their top pick, the candidate they would rank first. The only voting system we've talked about so far that is not based on ranking is approval voting, where you vote yes or no on each individual candidate. But all the other systems can be calculated, like the winner can be found or determined using the ranking of the candidates. And so whatever the underlying scheme is, that's not really all that important. The work of Kenneth Arrow applies to anything where ranking forms the basis of that election system. So when we talk about a voting system, that is defined as any process that takes a collection of ballots and it combines the information on those ballots according to some rules of a method that's chosen, and combining the results in this specific way produces a winner, or of course it could produce multiple winners. We could have an election, say, where the top two finishers are declared winners, for example. But so a voting system is just any process that takes ballots, combines the information on those ballots using a specific method, and it results in having a winner declared at the end. Now, the work of Kenneth Arrow made two big assumptions. Firstly, it assumed that the ballots are preference ranking ballots. So everyone turns in a ballot where they have ranked the candidates from first pick to last pick. And Kenneth Arrow did allow for something a bit more general than what we've discussed, in that the work allows you to tie rankings. And what that means is you could rank two candidates in first place and two candidates in second place. We're not going to go into the math of how that works, just understand that the work of Arrow is a lot more general than just what we've discussed in class. Second assumption is that voters are consistent. Now, in the real world, this may not always be the case, but what we mean by consistency is if there are two candidates, let's call them candidate A and candidate B, then regardless of who else is in the election, whether there's no one else or whether there are 20 other candidates, whoever else is in the election, you will always rank candidate A and candidate B in the same way relative to one another. So you will always rank, for example, candidate A above candidate B. If they're the only two candidates in the election, you will rank A above B. If there are 50 other candidates, you will still rank A above B. It doesn't matter where the others slot in, as long as A is still ranked above B. That's what we mean by consistency, that you cannot somehow introduce a different candidate into the election that will cause your ordering of A and B to flip so that now suddenly B gets ranked first. Now, Arrow defined 4 properties for an ideal voting system. First property is called universal domain. All universal domain means is if you are filling out a ballot, you can order the candidates in any way that you want. There is no restriction on how you order the candidates. No one says to you, you cannot take candidate A and rank them third. If there are 3 slots, you can rank candidate A in first place or second place or third place. There are no restrictions. Second property is Pareto optimality. What this means is that if we're looking at an election with 2 candidates, A and B, maybe other candidates, maybe not, but if all voters prefer candidate A over candidate B, then when we combine the ballots, B shouldn't come out ahead of A. So if everyone chooses A over B, then the system that combines the votes shouldn't somehow favor B over A. Third property is non-dictatorship. That means that no individual should be able to dominate the election. So no one's ballot should be more influential than anyone else's ballot. And so that essentially non-dictatorship means there isn't someone who can single-handedly determine the outcome of the election. And finally, the fourth property that Arrow came up with is the independence from irrelevant alternatives. What this means is, again, if we have candidates A and B, and in the election that we run, A wins over B, and someone says, oh, we forgot to put candidate C on the ballot, and you introduce candidate C and rerun the election, it shouldn't cause the winner to now switch from B to A. So putting in a third candidate shouldn't cause the results to flip around. I know this sounds a lot like Pareto optimality, but the two are slightly different. And we'll look at a couple of examples that will emphasize the difference here. Now, Arrow defined those 4 properties and said those are the properties we want to have in an ideal voting system. A voting system is good if those 4 properties are satisfied. Well, then Arrow went ahead and proved what is now called Arrow's impossibility theorem. That says, there is no voting method based on rankings that satisfies the properties of universal domain, Pareto optimality, non-dictatorship, and independence from irrelevant alternatives. Read that again carefully. Those 4 properties that we want in an ideal voting system. Arrow proved that no system based on rankings can satisfy all 4 of these properties. So anytime you are working with a voting system that uses rankings or that is equivalent to rankings, even if you're not directly ranking, if it's equivalent to ranking candidates, then that system cannot satisfy all the properties of an ideal voting system. So there is no fair voting system. A fair voting system does not exist if we want these 4 properties to be satisfied and the ballots use rankings or are equivalent to rankings. Of course, we could define different properties. those four properties are not the only ones that we may want in an ideal voting system. Just remember, we already have said no voting system is going to satisfy all four of those properties if rankings are involved. Now we're talking about adding even more properties. So it's impossible to find a voting system that satisfies all of these properties, but maybe you can decide which properties are really important to you. And there may be voting systems that satisfy some of the properties, if not all of the properties. So what other desirable properties may we have in a fair voting system? One of them is anonymity, meaning each voter's ballot receives the same treatment or weight. No one's ballot is treated more importantly than anyone else's ballot. And secondly, neutrality, which means each candidate receives equal treatment. So no one's placed in a preferred spot on the ballot. This could, for example, be, there are actually some elections run in the US where if the person who currently holds an office is running in the election, their name appears first on the ballot. The name that appears first on the ballot is in a preferential position. So that would be an example of not having neutrality in an election, by placing someone in a preferential spot. Now, remember that Arrow's work was from the 1940s. In the 1970s, two independent scientists, Gibbard and Satterthwaite, proved that any voting system, other than a dictatorship that's based on rankings, will sometimes have it be possible that one voter can receive a more desirable outcome through strategic voting. As this doesn't say that a voter can always get a more desirable outcome. They just proved that in these voting systems, it will sometimes be possible for a voter to be strategic. Maybe in some of the examples we've seen, you could rank a choice you like more lower on the ballot, and in that way actually have your first choice come out on top. That was an example of what they proved. And if you want to study how voters can act strategically, that gets into the realm of game theory, a mathematical field that is pretty interesting. I believe the book has a chapter on it if you're interested, but we're not going to get to that in Junta. So let's just look at two examples here. First example, does the plurality method satisfy the Pareto optimality condition? Now, remember, what does Pareto optimality mean? If all the voters prefer candidate A over candidate B, then the system should not favor candidate B. Candidate A should come out ahead. So what will we have in a plurality system? If the two candidates A and B are on the ballot, candidate A will always be ranked higher than candidate B, which means if candidate A is someone's first choice, they will vote for them in a plurality system. If they have a different first choice, they're not voting for A or B. That just would mean that B is not going to receive any votes, right? It's impossible in this system for B to receive any votes in a plurality election because people will either vote for candidate A or some different candidate. And so candidate B will have 0 first place finishes. So we can't guarantee that candidate A wins the election, but candidate B cannot win the election. And so that is Pareto optimality here. Candidate B cannot come out ahead of candidate A. Candidate A has the potential to win this election. Someone else has the potential to win this election, but not candidate B, because candidate B is always ranked lower than A, and so will never receive any votes. Now, I said it's sometimes a bit difficult to just understand the nuance between Pareto optimality and independence from irrelevant alternatives. So that example we just looked at illustrated Pareto optimality. Now we're going to look at independence from irrelevant alternatives. Say an election has two candidates, A and B. There are 7 voters. By a margin of 4-3, they choose candidate A over candidate B. So in a 2-candidate election, A wins. A wins this plurality election with 4-3. Now we're rerunning the same election and we're adding a new candidate C to the race. So firstly, what we find is of the candidates or of the voters who voted for B, no B voters prefer C over B. So of the B voters, they would still rank B as their first choice. And then we had the candidates who had A as their first choice. And then, of course, C could also be the first choice. So of the voters who had A first, 2 of them now rank C as their first choice. The remaining 2 still rank A as their first choice. And 3 rank B as their first choice. Doesn't really matter what happens with the rest of the rankings here. We're only interested in, since it's a plurality election, who gets ranked first. But what happens in this election now? Suddenly, candidate A is only receiving 2 votes and candidate B is receiving 3 votes. So B wins with 3 votes. So we added a new alternative and it flipped the outcome of the election. Even though more people prefer A to B, this third alternative caused the election outcome to flip. So this is a violation of independence from irrelevant alternatives. So plurality elections do not have independence from irrelevant alternatives. And we will briefly talk through some more examples of this in our next live Zoom session.